Mhm. Mhm. So, good evening, everyone. Mm, so, today is the week number 10 of problem solving session. So, previous day, actually, due to my internet connection and everything, so I was not able to conduct the session. But I guess like some people will join afterwards. And due to this change of time, I guess there is this less number of students and everything. Okay, that's fine. So let's start with this. This is the problem solving session week number 10 for Sensors and Actuators course. And my name is Shomnath Bhattacharjee. I am currently pursuing my PhD in the Department of Electrical Engineering, IIT Jodhpur. And my research interest is toward fabrication of flexible and organic transistors, where I use different kind of flexible substrates. And on top of that, I try to fabricate transistors and towards simulation of neuromorphic computing applications, so towards simulation of synaptic behavior and everything. So this week was a bit delayed and everything, so because of that the our everyday schedule is on Sundays from 6 to 8, and so this week we have rescheduled the class. So this is the basic course layout where we have learned about these things so far, and now we are gonna learn about this. Just a second, let me change the colors like this. Right. Yeah, so we'll today learn about this mechanical phenotyping tissues of biochip. So most of most of the classes in this course was most of the videos in this week was towards demonstration purposes and everything, but for our purposes we'll need to learn more about different types of spin coating and these kind of techniques, and where we have already discussed about this spin coating and everything, but we'll learn more in depth things about this spin coating techniques and everything. And afterwards we'll move towards more in-depth discussion of PVD techniques. In the videos, it was there. So, the technician was in the video who installed the machine and everything. But that was towards more installation and everything. That is not for our research purposes. So, we'll learn about this how to use this PVD techniques and everything. So let's see this. So we'll recap and go more in depth towards spin coating techniques, and we'll recap the thermal evaporation technique, and we'll move more in depth to the thermal evaporation techniques as well. So first, to start with spin coating techniques. So the basic spin coating technique is like this. So where so this is the spin coated in our lab, where you can see that it's I guess it's visible, yeah. So the speed is set at 100 rpm. Oh, sorry. The speed is set at 100 rpm, and the acceleration is 200 rpm per second. So the speed is, I guess I have to reduce the brush size, but that's it. And the duration is 30 seconds, so that's half a minute. And so this is the basic thing, and we have steps as well, so we can have one step, two step, or three steps as well. So let us discuss about this. So the basic thing about this spin coating is we have several parameters, right? So first of all, we can change the speed, that is the spin or the this thing, I guess, yeah. So the basic thing is that first we drop the material. So this is our material that is directly on top of this sample. So this is our sample, this glass substrate is our sample. On top of that, we are just pouring our solution, the prepared solution that is already prepared by a specific measurements and those kind of things. And then afterwards, what we are doing is that we are giving it a rotation, so it is rotating with the speed of omega, that is this thing. So you can see, right, the speed is 100 rpm here. So this 100 rpm is nothing but this speed. So it is 100 rpm to, you can go above like 300 3000 4000 rpms and everything. So, and then we have the acceleration value. So what is acceleration? The change in this values. So it is set here as, just a second, it is set here as 200. So based on different kind of a thing, so you can set it, sorry, just a second, yeah. So it's set at 200 rpm, but whereas it can be like 500 rpm, let's say. So like the starting speed will be like, so with if we don't have a specific acceleration, so what will happen is that our starting speed is zero tick. So now at time t0, what happens is it suddenly starts to increase directly to 3000. It will work for, let's say, 30 seconds. So the time duration is like 30 seconds. So what will happen, it will stay there for a bit, that is for 30 seconds. So for 30 seconds it will stay there, and afterwards what will happen is that at t equals to 30 it will be at 0 again. So this is our 3000. But with acceleration speed and everything, so it will gradually increase, and the increasing speed can be like, can be changed and everything. So based on this, it will gradually increase and change. Now, so this is a single step thing, right? So what we can do in this case as well, so we can have a multi-step spin coating. So for several materials and everything, so we can have a multi sorry, we can, just a second, what's happening, yeah. So for like multi-step, we can have our first step, second step, third step. So what can be done in this case of this spin coating, we can have this step as step 1. While we change to step 2, it will have a different speed. We can set the speed, we can set the acceleration, and we can set the duration as well. So let's say, okay, so let's say we have a spin coating with a very small rotation speed, like let's say 1000. So we have 1000 rpm for 10 seconds. So before spinning it with a very high rotation speed and everything, what we'll do is that we'll give it like this. And the acceleration is same for both, let's say 500 acceleration for both of them. Now for the second step, what we'll do is that we'll change the speed to, let's say, 4000. So if there is a bit of addition between the sample and the solution, what it will do, that it will stick on top of the surface for 1000, and then it will start spinning rapidly. So it will create a very thin layer of that. So let's say this is for 20 seconds. So it will look like this. So like while this is starting directly, it will go to a 10-second stage, and afterwards it will suddenly rise to 4000. Then there it will stay for 20 seconds, and then it will gradually decrease. So these kind of process techniques may be required for several types of solutions and several types of device fabrication as well, where will look towards getting a very uh, very good and very uniform film. So where we would like to have like this two stage of thing. So this is the first stage and this is the second stage. So this is called a multi-step thing. Now afterwards what we'll do is that afterwards we'll just give like based on different materials and everything, so we'll anneal it. So like the deposited layer will be annealed and it will be heated, and then like the excess solvent will be evaporated and the film will be situated there. So like for several different kind of materials we may have a annealing stage for, let's say, if we need a very gradual annealing, let's say, we can have a 20 or a 25-degree centigrade, and we can give it for, let's say, 2 days or something like that. So it is a gradual. And for some cases, if we need a rapid annealing thing, so we can give it to, let's say, 150 degree for, but for only 10 minutes or something like that. So based on your material, based on your device, and based on your like different design techniques and your choices, and based on your application as well, obviously. But like you can change this, and you can move towards like having a multi-step or a single step. The speed, the acceleration, the time, and everything you can modify based on your need. And now you will have a total total layer that can be modified with your knowledge and everything. So you can optimize everything here. Okay. Now, apart from the spin coating techniques, we have several other several other solution based techniques. So here I am showing that the gradual evaporation of the solvent and everything. So the deposited layer will be this uniform. Although it's uniform while we are seeing with our bare eyes and everything, but it's not as uniform as any PVD grown layers or something like that, the thermally grown layers, or even like any kind of a a deposited layer or something. Okay. Now what we have is another other types of this solution deposition techniques, where we can have different kind of a technique. So for several materials we are unable to use this solution. Let me write this first. So for different solution processing techniques, so like there are several solutions and everything, where, just a second. So for different solution processing techniques and everything, so we might not have a possibility to use spin coating. So if our spin coating is not suitable, let's say, so what we'll do, we'll use other different kind of a technique. So what we can do is like we can either drop cast. So as the name suggests, drop casting is dropping the material. Okay. So now dropping the material, either you can say drop by drop, so it will mean a drop cast, or you can have a solution cast, where you will drop the material, or this not the material. So like let me just rephrase it. So dropping the solution drop by drop, and while solution casting you will drop the solution, and you will put it in a beaker or a petri dish or something like that, and it will form a thick layer of this. So this is called solution casting technique. So there are several kind of a techniques, but for several as in my work, like I have to deposit very thin layers of semi organic semiconducting materials. So in those cases what we have to do is that we have to use drop casting technique, where we just directly put the sample inside this, and we just directly put on top of. So here I am showing you an basic glass glass slide, whereas like it here you will have your sample. So you will just drop the solution on top of your sample, and it will form a puddle like of thing. Now for drop casted materials and everything, in most of the cases we don't annihilate, but there might be some annealing. So we'll just remove the excess solvent, and there will be only the remaining solute there. And based on that, so like I am here showing the crystal formation. So like for organic semiconducting like organic semiconductors and everything. So after like drying off and everything, so there will be this kind of a crystal formation, which will be like which will give us the basic semiconducting nature of this material and everything. So you can see, right? So this is semiconductor crystals. So this is a polycrystalline semiconductor like thing. So and based on that, the crystalline forms. So this is one of the basic techniques to like drop cast organic semiconductor or something. Apart from that, there are several other materials where we either drop cast it or spin coat it or solution cast it. So there are several solution pressing techniques. But what is the major disadvantage with this kind of a techniques is that their uniformity. So the uniformity is very poor in all of the cases. So the uniformity is not there, and because of that, we'll need a PVD technique. Now, what is the main advantage of these kind of a techniques are? Or let me write it down using this. So one of the main or major plus points of these, one of the major advantages of these kind of a techniques are towards like low cost systems and everything, right? So for being low cost, why? Because it requires a very low amount of electricity, and the cost of these equipments, so like low cost towards both, right? So low cost towards the equipment cost. The equipment cost is very low as well, because we don't like we need a very specific area where it has some vacuum and it will just stuck on the chuck the sample will be stuck, and after rotating it and everything, so like you need to rotate it and everything, so that's it. Otherwise you don't need a very dedicated like environment that you need plasma, create plasma, or you need a very high vacuum or something like that. So it's not necessary in those cases. Just a second. So now, apart from that, the operational costs are also low, like the electricity and like to maintain the equipment and everything, the operational cost is very low as well. So these are the major things that it is for low cost electronics and everything. So but you need to know that a spin coater is like a 8-inch wafer size, right? So to use a 8-inch wafer it's fine, but beyond that, or let's say it's for 4-inch, so the total size is 8-inch, but to like if your sample is very small, it will be more uniformly thing. So because like you can see, right, like we are dropping the sample in the middle of the sample, right? So if the solution is put on the middle of the sample, there will be a gradual height change in these cases, right? The major thickness will be at the center of the sample, whereas towards the edge of the sample it will be the much thinner and everything. So so if the sample is very small, let's say like this change or this thickness deviation is very negligible, so we can use it. But while we are going towards, let's say, a 8-inch wafer, it will be a hassle to use. Okay. So there are several disadvantages and advantages as well. So based on that, we need to have a PVD technique. Now with the PVD techniques, there are several problems as well, right? So one of the most used and one of the most low cost. So like if you are moving towards, let's say, a sputtering technique or something like that, it will cost you more. So I'm not going into details of sputtering because I have already discussed it in the, I guess, the second last class. So like I'm not going into sputtering, but the problem with sputtering is that it is a very high cost thing, right? It obviously gives one of the most uniform films you can get, but the problem with that is that it is high cost and the maintenance cost is very high. It usually gets like you need to keep it in a very clean and everything place, and the usage cost and everything is very high as well, right? Now to solve this issue and everything, so like one of the best ways to use is obviously a thermal evaporator. So we have a thermal evaporator. So this is a thermal evaporator from Semicore, and we have it in our lab. So I am just describing it through the thermal evaporation process is described through this. Now like in most of the labs and everything, we have a very I would not say it is old, but like directly, so like you need to use the thermal evaporator manually, right? So there might be some manual processes, there might be some automatic ones, and you can also use it in a manual slash automatic way, right? Now this one is an automatic one. So because you can see, right, you have an entire control panel and everything. You have an remote control panel and with these things and everything. So you have a total control panel which through which you can just completely have access to all the necessary equipments inside the chamber and all things, right? So with like let's say the more manual ones, we have like switch boxes and everything. So you will have switch for each of the things. So for rough pumping you will have a switch, for each valve you will have a switch and everything. But in this case you can see, right, the schematic is not entirely visible, but you can see. So this is our mechanical pump, this one is our mechanical pump, and everything is connected with this. And so this is the thing. So I'm not sure if it's visible enough or not, but like we have an entire process saved here. While we can also do a thing, so I don't know if it's visible or not, but sorry, just a second, where is it? Yeah, so it's visible or not, but we can pump the chamber with a single switch as well. So if you need to pump the chamber, so what is pumping the chamber? Pumping the chamber means like we are just creating a basic vacuum that is through the mechanical pump. So the pumping chamber means that we can ideally directly like use each of the valves directly and click on top of it. Or otherwise what we can do is that we can click on the pump and it will start or off, right? And there are also like several like protocols as well for these kind of automatic systems, that like if the valve is not open or if the valve is open, the pump will on or pump will not turn on. So there are several factors as well. So these are the things that an automatic system have. But in case of a manual system, let's say you have a manual system and you have these kind of a board, right? So you need to remember that you need to turn on the valve before turning on the pump and these kind of things, right? So there are several useful cases and everything. Now, so this is a very basic system and everything. So this the system costs, like the system cost is very high obviously. Otherwise, like if you compromise with the system cost, then you will have to like this will be a hassle, right? So if you are like trying to like use this machine for deposition or something of that kind, then you will have to remember more, you have to be more professional in these things. For a system this easy, you can have an automatic system. You just remember to turn on this after that, and there's a very simple process flow and these kind of a things, right? Now, apart from the system cost, the maintenance cost is also high. So the maintenance cost is high, and like there are several things like different metals and these kind of things. We have to deposit them through evaporation techniques, either through thermal, either through sputtering or something like that. But we have to do it like that because they are not solution processable, because so like not entirely metal. So solution, wait, I did surely it's not working. So they are non-solution processable. So for these kind of a things we have to anyways use uh thermal evaporator or sputtering or these kind of a systems. Now for thermal evaporator, the first step we need to have is that we need to first ensure that our sample is inside this chamber, our boat is working and everything. So we need to fix this boat on place. So for different kind of a materials, you might have different kind of a boards and everything. So for, let's say, for gold you have a separate board. For silver, you, because like after every usage and everything there will be some residue left. So like if there is some gold left, so if you can't deposit silver silver on top of that, right? So what you will do, you will have to use gold, and now you have to remove this boat. And sorry, now you have to remove this boat and then change it to the appropriate boat needed, right? Now, and the boat is this thing, right? This restive boat. Okay. Now the next process is that after changing the boat and everything, you need to measure your amount of of either silver or gold or something like that. For, let's say, for a metal we are depositing and everything, so for that you need to like select the amount and everything. Now after selecting the amount, you are just putting it inside that, so that will be our step 2. And we'll just fix our samples here. So this is our step 3. We'll just stick the samples on top of this chuck or the substrate holder, and we'll just fix that, at which position do we need our sample to be in, right? Now afterwards what we can do is that we'll just close the chamber and everything, and then, so this is our chamber, right? This thing is our chamber. This thing is our chamber. So everything I'm talking about is inside this chamber, and we have a viewing mirror and everything. So if we want to see inside that, we can see it. So while deposition and everything, we can see most of the insides and everything, but it will be in a like a purple hue or something like that because of the plasma environment and everything, right? Now after that, we'll have to attain, so we have vacuum pumps and different kind of a pumps. So we have turbo pump and a mechanical pump. So we have two types of pumps: a mechanical one and a turbo one, right? Now, so first, that our total samples and materials and everything is inside this chamber. We are just closing it, and now we have to attain we have to attain a temperature, uh, not temperature, sorry, pressure, where we'll have we need a specific environment where we can deposit our deposit our metal on top of our sample, right? So first we need to create this vacuum. So at first the mechanical pumps goes, and it will create a vacuum up to 10 to the power minus 2 torrs. Afterwards what we'll do is that after utilizing the valves and etc and those things, we'll change it to the turbo, and that will help us to achieve 10 to the minus 6 torrs. Now this 10 to the minus 6 torrs uh, like is a suitable pressure to deposit gold or something like that, or silver, let's say. So after attaining this, that is our fourth step. After attaining that, what we'll do is that we'll start heating this boat, right? How to heat that board? So to from utilizing this filament transformer, you will heat that board. So everything can be controlled through this. We can check it here, and on the other page we'll have another control for this filament transformer and everything. So we can directly just heat it up, and we can, based on the given current on top of this resistive filament and everything, the boat will get heated and it will start depositing. So like at a certain threshold, this will start depositing, and by increasing that amount of heat provided, we can increase the deposition rate. And based on our needed thickness and needed precision and everything, we'll start it. So before that, we also have a shutter. So I guess it's visible. So this is a short shutter. This looks like this. something like this. Not like this, sorry, just a second. So it looks something like this, a triangular shaped thing. And what it does is that we can just rotate it, right? So the boat is just below this. So here is a, let's say your boat is connected both sided. And now what we can do is that either we can close the boat, then if even if the material is getting heated and getting deposited, it will be deposited on top of the shuttle itself, but not on top of your sample. If you need a specific deposition rate, and if you need a very specific uniformity, and if you need to calculate your thickness directly from itself, so like we have already learned about different like measuring techniques, let's say like the profilometer, the profilometry, the ellipsometry, and these kind of a things. But if let's say you need to have like your deposition at a certain deposition rate and everything, so you will have to utilize this shutter. So after achieving a certain, like let's say constant deposition rate, will change the position of this shutter, and based on that the deposition will start. Now, so after achieving this deposition state, so this is our number 5, and after achieving this desired amount of deposition, what we'll do is that we'll reverse everything. So how to reverse everything? First we'll leave that for some time, and afterwards what we'll do is that we'll first close this source after this deposition technique and everything, so everything will be backwards. Now after that, what we'll do is that we'll again use the turbo. So after achieving that thing and everything, so the turbo is turned on, right? So we'll have to turn off this turbo, and after that it will come back towards this thing. So we'll turn off this mechanical pump and everything, and after that we can open our door, and then we can remove our samples from here. We can remove our boat, and if let's say your next person needs to use it, so they can use it directly, right? So this is the basic process steps of a thermal evaporation system. Now apart from that, so there might be, so based on different machines, different like different instruments, you might have some different steps as well. So for like for the manual ones and everything, so you need to control each of the valves separately. And if you need to control it if it's entirely automatic and everything, you just need to set your temperature, you need to um set your deposition amount and everything. So apart from that, so on both of the sides here, here and here, inside the chamber obviously, there are, sorry, just a second, so there are quartz crystal monitors, QCMs. So these are used for measuring the deposition thickness. So how they work is that they can see this, and by this they can measure that how much deposition is going on. Now the problem with this quartz crystal monitors are that we need a certain amount of threshold health to correctly judge how much is deposited or not. So if the health is 90% of the full amount, that the initial amount or something, so what will happen is that it will give a certain amount of deviation from the real result. So let's say the SD is, let's say, plus minus something like 1 nanometer or something. So for some cases it will be very fatal, and for some cases it will be negligible and everything, right? So based on these use cases and everything, so we might have to like replace the quartz crystal monitor as well. So let's say if it's beyond 75% or something, it will be like it will be unusable, so we have to remove and like change it, right? So there are several different things you need to remember. Now I guess you can see this hole here, right? The hole is visible. Now what is this? So like we have sent it for repairing and everything. So this was e-beam source. So this is a dual system that have the capability of thermal evaporation and e-beam evaporation. Now this e-beam system, what it can do is that, just a second. Now this e-beam system, what it can do is that it can provide e-beam as well. So everything will be here as well. So and the e-beam system will just directly process the like proceed to heat it. Now with that thing, like I need to mention that we need a different kind of a boat and different material of boat, so we need to change it as well. So based on the e-beam or the thermal processing and everything, we need to change the boat, we need to change the amount of material being used. And so like we have to optimize the steps. So how much amount do we need to put to get a optimum amount of material to be like deposited? Now for that there are several cases. So like as gold is costly, let's say as there are several costlier things, so we need to like use it in a very measured amount and everything. So for each deposition we need to optimize that, how much uniformity is required and how much precision is required while depositing this gold. So we can also like optimize our vacuum inside the system as well. And apart from that, how much time is required, how much time do we have and everything. So we can achieve this based on the system's performance and everything. So we can have like different amounts of um the pressure inside the system itself. So based on our use case and everything, we can modify it and we can optimize it, right? Now after that, apart from that, so right, so this was it. So this was it for today, so where we have learned about this recap of this thermal evaporation and the process steps and everything. And we have learned about other deposition techniques, like solution deposition techniques, like the spin coating, the drop casting, and we have also talked about the solution casting as well. So if you have any question you can ask me, otherwise we'll move towards this question answers.
Hello,
Sir,
sir.
I haven't.
Yeah,
Okay, yeah, go ahead, go ahead.
Sir, I haven't query, sir.
yeah, sure.
Sir, uh, in this deposition technique, sir,
Hmm,
when I am using the glass as the substrate material, 4-inch glass
hmm,
substrate mean,
hmm.
um, it's sir, it's glass substrate is available, sir.
like can, can you repeat your question? I was unable to get it.
In searching in online, I
Hmm,
find the substrate like silicon substrate. They're
hmm.
available, sir.
Yeah.
It's cost around 6,600 rupees onwards, sir.
Hmm.
But
Yeah, so for
I
that as well, like you need to use a very good quality silicon as well, because otherwise, otherwise there will be problems with the device, afterwards. So like
yes,
if
sir.
you go
But
towards better quality and
I
everything.
can I wanted to make this device in glass as the substrate material. Mean
Okay,
this
okay.
16-inch glass substrate mean there is no proper reference for that, sir. We can implement the glass material similarly to this, sir, in thermal evaporation
Like
technique.
I have worked with glass and everything as well. So as my research is towards flexible electronics, right? So
Yes,
I've been using plastics, glass and everything. So for that, there are two separate things. But are you asking about how to purchase this glass, or can we use it?
sir. I haven't two doubts, sir. How first one is how to purchase this glass substrate
Okay.
in 4-inch or 3-inch wafer,
So
and
no. So for most of the cases, what we do is that we get a glass that is deposited with already a side of the glass is normal glass, and a side of the glass is either any kind of oxide coated or something like that. So you can purchase something called a FTO glass. So fluorine tin oxide coated glass, where the glass one side of the glass is completely conductive, that is because it's coated with fluorine tin oxide.
yes, sir.
So I have used that fluorine tin oxide or even indium tin oxide coated glasses, where you can directly purchase these glasses. I'm not sure about the price right now, but it's a bit costly. But you will have a total the size. Let me just check that. Just a second. I guess the size was about 1 inch by 1 inch or 1.5 inch by 1.5 inch. I don't remember it. that correctly, but
Yes, yes.
so like you can purchase that thing, and what you can do is that you can cut the glasses based on your like use case. So if you need the glass by 4 inch by 4 inch, you can cut it, or something like that. So we generally use a 2 inch by 2 inch one. So what we use is that we purchase this complete glass of a 1.5 feet by 1.5 feet, and then we get it cut by some machines and everything in the mechanical department, and so we get this 2 inch by 2 inch sizes of these things.
Yes, sir.
So and what was your second question?
In my second question, flexible MEMS for phonotypic tissue properties, sir. It
Yeah,
is in the like the type. Sir told. Um, uh, Sir used the soft bake and the hard bake for the entire process, sir. By loading the mask and after, before loading the mask and after loading the mask, we perform both the soft and hard bake. Why
yeah.
it needs, sir? It's a creepy question, but it's by speeding this, it's also it's to make it's yeah, it's a doubt, sir.
So your question is
Sir, why?
why?
Yes, sir.
Yeah. So your question is
Yes,
why do we need soft bake and hard bake in this case?
yes, sir.
So like it's exactly same as like why do we need soft bake and hard bake for any kind of a like any kind of a system things, like let's say you are doing photolithography, why do we need a soft bake and a hard bake? So like
Yes, sir. Yes, sir.
it's entirely similar, there's nothing difference in between.
No, sir. No, sir. We can perform the photolithography. Mean we can use directly load the mask, expose UV, uh, then perform hard bake. It's easy now because to reduce the time consuming, we can skip the soft bake, sir.
That's based on how much detail do you have in your mask itself. So like obviously you are saying right, so for like if you don't have a very smooth details, fine details and everything inside your mask, it's best to use directly the hard bake. But the process, so like in lab we do many things that is not directly goes with the processing and everything. So like if you need to make the design very fast and everything, and you know that with the soft baking in your case, in your application and everything, it's that much not necessary. So what you can do is that you can skip this step. That is based on your application and based on your design sizes and everything, right? So that's entirely on you. But for like the basic process is obviously containing that with a soft baking process, because that's necessary in so many cases. So like in most of the cases, if you want to completely attain the design and everything with very much precision and everything, so you need to have a soft baking process.
Thank you, sir.
Yeah. And from your side there was another question.
Hello, sir. I'm
Yeah,
Krishna here.
yeah,
Actually, it is not a question.
yeah,
So, my general feeling is that this I took this course as a part of robotics domain, thinking that I would know more about sensors and actuators and how to
yeah.
use it in applications. But somehow I find it is getting into so deep into fabrication and sensors
Excellent. Yeah.
and that lithography. It's a different domain. Sorry that actually the yeah I appreciate how it is fabricated these microelectronics and nanoelectronics, but I'm not a electronics engineer. So I'm just wondering whether I can make it up this course or not. That I just
Yeah, so the main aim of this course is towards knowing a bit of the sensors and actuators, but more towards how to fabricate them and how to modify and how to advance them, like based on your application and everything. So as per the last question as well, right? So you can modify and optimize your processes. So like let's say if I have a different kind of a pattern and everything, So I need to change the type of materials I used, I need to change the type of process I used. So similarly to that, like I am just analyzing that. So based on that, you can say that this is more towards how to fabricate or how to make the mems and nems.
Okay.
So
Okay.
that is
Okay.
more
Okay.
towards that. Yeah, the course
Okay. Okay.
content is
Yeah. Yeah. I got it, sir. I thought this course is more about using the sensors in various robotic applications. So, but what you are saying is more about making sensors of different configurations.
making sensors and actuators. So this is not about entirely about the like how these sensors and actuators are and how do we use them, but how to fabricate them and how to process them with our expertise and everything, and how to change them or how to modify them based on our application need and everything. So this is towards that.
Okay. Okay, sir. I will try my best. I will try to
Yeah, yeah,
get
obviously,
some
best of luck. Like
overview. Some, I think, by listening to that, by reading, some vocabulary goes into my head. I hope I could answer, even though I'm just a mechanical engineer.
fine, that's fine, because like I am like also from physics background. I am not like from any kind of electronics background. So like I can also like this is my brief, right? Educational background is towards physics.
Yes,
So I
yes.
have completed
This is all
BSc and
physics
everything.
only. This is
Yeah,
physics of semiconductors, physics of vapor fabrication, real. Okay, all that. Okay. Anyway, sir, I
not
appreciate.
entirely
Please
that.
go
So
ahead.
I am towards more towards like proper theoretical physics, the classical mechanics and those kind of a things. And like I have completed BSc and MSc. So I have completed like science basis of that. So quantum mechanics, theoretical physics and everything. So I didn't have any kind of a basic idea of how these fabrication things work, and so about these things, right? But like with getting used to how to fabricate, because like we need to implement these kind of a sensors on some kind of application. So my application is towards implementing a brain inspired circuit, but to make that I need like basic idea how to fabricate these things and everything. So
For
that's it.
example, sir, you are saying about flexible electronics. That means some kind of electronics fabricated into the textiles, garments.
Yeah, so
So, I think.
this is broad. So like you have several like indigestible electronics as well digestible electronics. So where
Yeah.
like you digest the electronic parts and you have several like key components like nanorobots or something like that, and it goes directly to your body
Yeah,
and you
yeah, yeah. I
yeah,
heard a lot of developments are happening. Like
yeah,
even the pills, the electronic pills, they
yes,
can
yes,
track
yes, yes.
the drug release and
Yeah.
digest into the
So that
body.
that that is towards digestible electronics. There are several important domains like brain-inspired computing and neuromorphic computing, where like we are trying to implement a brain circuit. That is, a brain has several numbers of neurons and synapses, right? So based on that, like you can implement directly
Yeah, yeah,
synapse. So
yeah,
synapse is
yeah,
the connection
yeah,
between two
yeah.
neurons, and then you can implement that through a memory or a transistor and everything. So
Yes,
you
yes,
you can
yes, yes.
have that. So like
Yeah.
people are trying different kind of a things with that, and the
Yes,
most
yes, sir.
important thing is taking
Yeah,
your
yeah.
course is very
Yeah.
low cost.
Yeah, I actually retired from. I was not a teacher, but I used to teach in BITS Pilani. There is one professor, Sanket Goyal. Okay, he does a lot of work in these sensors fabrication at BITS Pilani, Hyderabad campus.
Oh,
Okay,
Hyderabad campus. Okay, okay. I
yes,
was thinking about this Pilani campus, so like the
yeah.
Jodhpur campus.
Yes, that Sanket Goyal in Hyderabad, BITS Pilani. Maybe you can go to BITS Pilani Hyderabad website. And Sanket
Okay.
Goyal, he has done a lot of this exactly similar things. Okay, he has a
Okay.
lab and a lot of sensors he has fabricated, like
Hmm.
glucose sensor and digestible. So many things. I don't know. I only know the tap of the mind. Just for your reference. Yeah, that's it.
Yeah. So he is working with Crest, right?
Crest means
Semiconductor technologies, right? He is working in.
he's working in. I don't know. I don't know.
Yeah.
Maybe.
So like. He's working towards MEMS and microfluidics for semiconductor technologies, most
Ah,
probably.
yes, 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 yes.
Yes, right?
Something like
Yeah.
yes, yes.
Yeah, I have read some of his work and everything.
Mm,
So,
mm, mm.
but like I'm mostly associated with BITS Pilani, this like Rajasthan one, because like as my home institution is very near to that, so that's why I'm more like acquainted with like their work and everything.
Okay, okay, sir. Wish you all the best. Right. Go
Yeah,
ahead. Go
yeah,
ahead.
yeah. So like we'll start with the questions and everything. So the first question is question number one is. So I guess you can either like study these kind of a questions and any kind of related questions what I am like describing in the class as well, and also the questions that you are trying to face in the like quizzes, the weekly quizzes and everything. So I guess
Okay,
that will be helpful enough for like
okay, sir.
tackling the question in the final.
So, just for cracking the exam, I think I can only rely on the quizzes and assignments. And
Yeah,
yeah.
so not, like the basic things you can read, right? Like the photolithography processing and everything.
Yeah, yeah, the high level view I understand. What is mask, what is
That's
exposure,
fine enough.
and
That's fine enough. You don't need to
uh,
go very
but
deep into
all that,
this.
for example, whatever you have shared, a lot of things, ion beam scattering, sputtering for
Yeah.
vapor deposition, what is the difference between that, which is advantages in which, that is getting into a depth. I know at a very high level what each one is used for what. For example, etching is used to remove the remaining material, etc. It's a very layman's, like salesman's talk, and I
Yeah,
am telling you.
fine. That's enough of that. So like you don't need to go very into these of things. So like as like I am like researching on these kind of a things, right? So I need to like go beyond these kind of a things, and like I need to know like these in very depth. But for a basic understanding and how to like prepare a very basic sensor or a very basic actuator and everything for your need, and to like use it in a circuit and everything, you don't need to go beyond that. So a basic knowledge of photolithography is enough to know about photolithography,
Yes.
and a basic knowledge of, let's say,
Yes.
evaporation is enough. That's fine.
Yeah. Yes, yes. I think, yeah, let us start. Let us see if I can answer the
Yes,
quizzes.
yes, 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 sure. So which of the following is used as a photoresist stripper? Ethanol,
Uh,
BHF, IPA, none of the above.
Photoresist sniffer means smelling.
Stripper.
Mm.
So which is used to strip photoresist. So after your etching and everything, so you need to remove the like the residual photoresist. So how do we strip
Acetone,
that?
right? I understand acetone.
Yeah, acetone.
Acetone is not here.
No, acetone is not here. So the answer will be none of the above.
Oh,
So
so,
IPA is not powerful enough to clean that, but I guess everybody knows about IPA, right? IPA is like acetone is basically nothing but the nail polish remover.
yes, yes. Because I remember that word in previous quiz or somewhere.
Yes,
So,
yes. So acetone is basically the nail polish remover, and you can use it on top of any kind of a printed bottle or something like that, and it will remove that. But IPA is basically a very simple cleaning agent. So if if both of you have sometimes cleaned your phones, and before like using a screen guard on top of your phone and everything, like
oh, okay, okay. IPA means isopropyl alcohol.
isopropyl alcohol, right?
Okay, okay. I
So
got it.
that is isopropyl alcohol. That is
Yeah,
a basic cleaning agent that is
yeah.
not strong
Basically,
enough to resist a
basically.
photoresist.
Yes,
And
yes.
ethanol is which thing? Ethanol
Ethanol
is
is
a
a
very
fuel.
common thing.
Ethanol is a fuel like a petrol.
Yeah, ethanol
Uh,
is a fuel, and so IPA ethanol is not strong enough to remove the strip.
Sir,
And
BHF buffer hydrofluoric acid, sir,
yeah,
for
buffer
etching
hydro.
this silicon from the for to create the membrane like structure in silicon BHF.
Yes, so that is for etching silicon. But
but
so
not
what is the problem with using BHF then?
Yeah, it will wipe out totally. It is
Yes,
cleaning. It should be cleaning.
that's the answer actually. So it is very strong, and we don't require that much strong. And IPA and ethanol is very mild for the work to do. So acetone is the most suitable one. Now move towards question two. Now, so HMI was described as the control for the thermal evaporator. So what is the full form of this HMI? What is
No,
HMI?
in my world, it is called human machine interface. I don't know about in your world.
Yes, it is human machine interface. So what is it basically? What is human machine interface?
It's only a kind of control panel.
It's control panel, that's it.
Yes,
It's a
yes.
completely a control panel that is used to control this thing. So here you can see that for as I was talking about the manual ones. So for the manual ones, you have a control panel like this. So that is based on the switches and everything. So you need to turn something on, turn something off. You need to turn some valves, like rotate the valve switches and everything. So that is the basic control panel that is manually used. And while for this that we have in our lab and everything, so that is a complete touch panel and everything, so that is more visually easier to use and everything. So you don't need to be a very skilled user of these things to use this. Now for the second one, question number 3. So which properties of, sorry, breast tissues have been characterized using the, so in the videos you have seen this. So which property of the breast tissues were characterized using the fabricated piezoresistive sensors? Piezoresistive cantilevers. Resistive cantilevers.
Give
Tissue
option.
stiffness as well.
No, so like my
Tissue
question is
stiffness
like
sensor.
the
Give
options are either mechanical or electrical.
electrical, sir.
Mechanical, sir.
Mechanical. So the tissue
Yes,
stiffness
sir.
is working as a mechanical one, right? So why it's not is like easy to use the electrical one? This,
Electrical one measure the impedance of the tissue
yeah.
by placing the tissue on interdigital electrode to measure the impedance.
Mm.
But in mechanical, we measure the how the tissue stiffness is vary from normal tissue to cancerous one, sir.
So why is mechanical like using the mechanical property is a good one? Why? What is the problem with the electrical one?
It can false negative easily identified in electrical one, sir. Easily we can identify false negative problem.
Any other problems?
Maybe electrical is not advised for diagnostic. Maybe
Yeah.
because
Because for if you are going towards a non-invasive method on everything, so that will be a good thing. But for electrical measurement there is also other organs as well, and because of that, that may we don't know that how much the tissue is damaged and everything. So for breast tissue analyzing and everything, phenotyping and all these things, we don't know that how much current we need to provide and everything, so like it is not advisable for that. And the mechanical one is easier one as well. So for piezoresistive cantilevers, they use anyways the mechanical energy, so that is the best way to use, apart from this impedance method, because that is also not a standard method as well till now. People are researching on it obviously. impedance analyzers and impedance measurement techniques and everything. So moving on to this fourth one, the microsensor with dash is used for characterizing. I'm not writing the total question because you have already answered this. Or no, no, no. Let me write the question anyways. So characterizing the electrical properties of the breast tissue. So we have already got the answer, right? Interdigitated electrodes, that is IDE pattern electrodes. So why IDE is better than the normal ones? Like I have already discussed it, and it is a very common answer. But for like for Mr. Krishna, I guess.
Oh, yeah. Can you repeat, sir, the question?
Yeah, so like the answer is the answer to this question is that why microsensors like what we are using like to characterize the electrical properties of a breast tissue. So we have already got the answer, that is through ID patterned electrodes, right? So why do we need ID? Can we not use let's say a different kind of a pattern like the straight lines or something like that?
What is a IDE, sir? Expansion.
ID is in oh sorry, just let me write it down. Interdigitated electrodes. So they are interdigitated. What is the like what is the let's say what is the advantage of using ID over any different kind of a pattern?
Okay. Don't know, sir. It's just beyond my knowledge.
So ID have this, any other like anybody other want to try this?
Oh, capacitive interference. I don't know. Yeah. Mm.
The impedance to
Your voice is breaking, I guess. You can repeat it again.
it of high the of the digits.
Your voice is breaking again.
Type in the chat.
Yeah, that will be better. So what is the difference between these and this? Let's say. So we have a sensor like this, not entirely this. So like, let me remove this. Yeah. So if we have a sensor like this and the contact pad is, let's say outside and something like this in this side as well. And while we have something like this and this, it offers high impedance between interdigits. Why?
Capacitive coupling.
Yes. The total area and the total W by L. So I was talking about transistors, right? So we were talking about W by L. So the let's say in a like a chemical scientist perspective. So what is that the reaction sites are more here. That is just a second. Let me just a second. Yeah, sorry. Oh, just a second. Yeah, sorry for the disturbance. So what I was saying that the reaction sites are more here. That is that we have a more space here. That's it. So that's how the impedance is getting like increased in this case. And for a very small change in a very small amount of impedance, that will be like harder to detect as well. Now let's move on to the next one. That is question number 5. So which material is used as base material to provide better addition to AU or gold films during fabrication. So for any kind of a fabrication, which kind of a base material is used to provide a better addition?
So give choice.
So nickel, let me write down the full names. Tungsten, silver, and chromium.
I don't know, sir. Maybe goldsmiths could answer better. I'm joking.
Chromium. So why is it chromium? Because anyways we use we use anything as chrome gold. So for the contact making we use this chrome gold thing. But why do we need to use chromium?
Maybe chromium doesn't interact chemically.
So what about nickel, tungsten, and silver? Not only for these four materials, right? So I'm talking about like all the materials. Why chromium is one of the best ones? There are other ones as well, so I have discussed that as well, like titanium gold. So that is way better than chrome gold, but as we know that titanium is very costly one, so we are not using that. So based on the cost factor, there are like titanium and those things, but why chrome gold?
Maybe chromium. Maybe related to melting point. Or,
No.
yeah, maybe related to melting point.
So it
I
is because
corrosion.
of the
Yes.
high
Yes.
corrosion resistance and also high hardness as well.
Oh,
So for a
yes. High
longer
corrosion
duration of usage and
resistance.
everything, you need chrome, because we know that
Yes.
gold is the best possible metal to have, right? For any kind of a contact and
Yeah.
everything. So the
Yeah,
gold is the best possible contact to
that is
have.
ultimate. No,
Yeah.
yes. Yes.
So
But
this
yeah.
inert,
Generally, we hear, yeah, chemically not chromium coated. We always hear corrosion resistance, right? Yes,
yeah,
yes, right.
so chrome coated is the best thing to have because it is high corrosion resistance, and because so like we know that gold is chemically inert. Gold is the most like mostly used and very high conductive thing. So that's why gold is the gold. So that's why we say gold standard. So that means the gold is the best possible option, right? But it has a very, because of this chemically inertness, it has a very low adhesion to most of the surfaces and everything. So that's why we need a very thin layer of chrome. That is, so now if we just for the addition purposes, if we use let's say silver, now if the silver is melting away for like for some time or something, so you if you are fabricating a sensor and it is taking let's say 15-20 days and very high resource cost and everything is there, equipment cost is very high and everything, so you need to use the sensor for at least 2 3 4 years, right? So you need a material that is very highly corrosion resistance. So because of that we use chrome. And apart from that, another thing is that titanium gold, as I was talking about. So TiAu is another choice, but for that titanium is very high, like is very high in cost. So there is a issue with that. Chrome is very like
Sir, we also hear about the nickel, right? Nickel coated parts and all for
yeah, so
anti
nickel
corrosion.
coated parts for, but for gold, another thing is that like let me just check the values so that will be better. Just give me a second. For chromium the band gap is at, let me write it down. For chromium the band gap is between 2.3 to 3.0 EVs, right? And for, just a second, let me check it again. So based on the band gap thing, we use chromium as well. So let me check the band gap values. So I don't remember both the band gaps values that in detail. So and for gold the band gap values are, so this is going towards more towards electronics thing, and for the gold it is 2.4 to 3.4. This is for gold. So they are very similar in value as well, right? For, if you are like having an electronic engineer's perspective or something like that, so you can see that gold and chrome are very similar as per the, like the atom structure and everything. So the band gap is very similar. So they are better to be used together. So now for nickel, if I check that, the band gap is a bit like different from that. Just a second, let me check that. Yeah, so for nickel, the band gap is 3.6 to 4. So that doesn't completely align with the gold itself. The
So,
best
sir, what you're saying is the two metals should be homogeneous in properties.
homogeneous, not entirely,
Okay.
but yeah.
Okay.
So like stands should be there. So like as we were talking about the mechanical properties, right? Like the high corrosion resistance and hardness and these are kind of mechanical properties. So they need to be very similar to AU as well, but the cost should be like, needs to be much lower than AU and everything. Now if we use nickel, so nickel doesn't have a very high corrosion resistance, but if we are comparing the electronic properties as well, the chrome is very similar to AU as well. So that's why chrome gold is like creates the best matching like pair for any kind of a like contact like fabrication and these kind of a things.
Okay. Okay. Okay, sir.
Yeah. So moving on to the next one, question number 6. So is it true or false? Right now, breast cancer is the second largest. This is an FAQ kind of a thing, but let's so largest cause of cancer related, yeah, cancer related female deaths
I think that first largest maybe.
in the world. No,
Female
this is the
males.
second largest. So this is true.
Mm. Which is the first one?
I'm not sure. I have to check that. But this is the second largest one because if you are moving towards like female related like deaths, so like female deaths I'm talking about. So cancer related female deaths. So in most of the cases, there's also another like there's a misconception that it is the second largest cause of total deaths, but it is not. It is only for cancer related deaths. It's on the second number.
Yes, yes. I
Yeah,
think first maybe cervical. I don't know if it is woman. Okay.
yeah, cervixes or like
Hmm.
maybe I'm not sure. So now so it is related to photolithography to try to answer as well. So just a second. Soft and hard bake are performed at which temperatures? General, I am talking about general things, so that is not perfectly similar for each of the materials, but like what is a general thing?
Maybe around more than 1,000 degrees centigrade.
No, no, no. They're very like less numbers. So let me give you like options, I guess. So it 90 degrees C and 110 degrees C? Is it 110 degrees C and 90 degrees C? Is it 120 and 90? Or is it 90 and 120?
90 and 120, sir.
Which one?
90 and
90 and 110?
120, 1 minute hard bake and 120
Yeah.
hard plate soft bake.
So this is a very average value.
Near
Like
of
this is not for each of the materials, each of the photoresist and everything, but more in most of the materials it is done that.
Yeah, certainly soft will be less than hard
Yeah,
bake.
obviously, right. So there were two options as well. So like 90 and 110 and 90 and 120. So like hard bake is how much hard you need to know that. So it's basic data related question. Just a second. Let me. Question number, I guess it will be 8, right? So, turbo pump is used to provide the initial vacuum in any PVD systems. Is it true or false?
True, true, sir.
Others?
I can tell on what basis I have
Yeah,
said
sure,
of
sure.
this.
Go ahead.
Turbo means something very fast. So for vacuuming, you require a high capacity suction, which is
Turbo means very fast, right?
very
That's
fast.
perfect. So, do
So
you need the fast one like at the first, or do you need it at the final stages?
I don't. I said it is a vacuum. Vacuum means suction of air, and
So I am talking about I am talking about the initial vacuum, right? So do you need to vacuum it very fast? What will happen if your sample and materials are there and you are vacuuming it
oh,
very
okay,
fast?
okay, okay. I got it. If you vacuum it very fast, the whole material gets sucked out. Huh?
Yeah. So then what needs to be done is that you need to have a basic vacuum of 10 to the minus 2 torr, that is through your mechanical pump. So that is for the initial vacuum, and then afterwards for having the minus 10 10 to the minus 6 torr, you need to use the turbo pump, and that is why the another name of the turbo pump is turbo molecular pump. You don't need to have a very high vacuum at the very first, so you need to reach a certain threshold, and after that you can vacuum it very fast. So this is sorry, true.
I'm able to answer it with intuitive judgment. Actually, I have not read anything about it. About
That's fine,
it.
yeah. That is like we what we all need to do is that like we don't need to remember everything. So so as your basic intuition was right. So turbo means very fast, but the thing you need to understand that what will be the problem if we at the initial stages we vacuum it very fast. What will be the problem? So that is why. So at the very first stage of my PhD, what I thought of that was like the mechanical pump takes about half an hour, right? And after that, the turbo pumps takes 2 hours. So I was thinking if like getting to minus 10 to the minus 6 dot takes 2 hours, it should be best to use like 2 hours, right? So if we are just using the turbo pump directly, we can get it to 2 hours. We don't need to have 2.5 hours. So that was kind of a hoax because turbopumps just within a second it reaches to 10 to the minus 4, and because of that sudden change in the vacuum, it will distort the materials, it will distort your samples and everything. So you need to have a gradual change in temperature. So because of that as well, so like what I was saying that, so like even for temperature, if let's say your I'm not sure about the temperature itself, but let's say if you are depositing gold and you directly give it, let's say 400 degrees centigrade or something like that. I'm not sure about the temperature, right? So because like we use the value of voltage provided and everything. So I'm not sure about the temperature, but let's say we have a 400 degree centigrade. So the gold will suddenly melt and then it will evaporate together. So like at an instant, right? So what we need to do is like we'll need to go to 100 degree, then we need to go to 200 degree, and it will gradually start the evaporation process, and then it will create a uniform evaporation rate as well. So
Uh,
like we need to get a very uniform evaporation rate.
Sir, in a similar way, why do we need two pumps, mechanical and turbo? Same one pump, gradually they can increase the suction, right?
No, so like in most of the systems, we don't have a gradual thing. So like the turbo pumps mean we just turn it on and it starts to suck the air out. So like in our labs, I'm not sure about the other ones. In our labs, the turbo pump goes directly to 10 to the minus 4 within like let's say 4 to 5 seconds maximum. and then it will like it increases gradually, because like you are going towards 100 times less than this, right? So it takes more time. But the mechanical pumps directly goes towards, like, let's say 10 to the minus 1. That is very reasonable one, and then it gradually decreases. So like we don't have an exact control of the turbo pump or exact control of the mechanical pump. So there are several different pumps as well, but as like in the course there is no description of those, so I'm not talking about that. But there is another pump called diffusion pump. So that is a very good way to control both of them, because a single diffusion pump can work as a mechanical pump and can work as a turbo pump as well. But with diffusion pump, the problem is that we need to cool it down. So we need, let's say, some coolants like liquid nitrogen or something like that. So we need to cool it down, and then it can work as both. So there are several, and so like for like the very low cost systems, like very low cost systems which have only the diffusion pump, because you need a single pump, and that's why so it will be of low cost as well. Just a second, sorry. I'm not sure why it's happening. Yeah, so like let's move on to the next question, I guess. So question number, so question number 9 is, what is the reason for using PECVD for depositing silicon dioxide during fabrication of microcantilever? So why do we have used this PECVD to deposit silicon dioxide? There are other ways, right?
CVD means vapor.
Chemical
Can you
vapor deposition, right? So they
Sir, at low
we
temperature,
yes, for low temperature.
it low
So what
temperature it
we
works.
can we can deposit silicon dioxide.
no silicon dioxide require high temperature, right? Deposition.
Yeah, so no. The question is that why do we need to use PECVD? So through using PECVD, we can deposit in a very low temperature. So that's the right answer. But my question is that silicon, what is other ways to deposit silicon dioxide? One of the best ways, thermally growing, right? Thermally grown SiO2 layers, but they require a very high temperature. So that's why using PECVD is best to like grow the silicon dioxide, the depositing silicon dioxide at a very low temperature. And so just a second. And question number 10. So maybe we'll end it here. For question number 10, answer it. So for ID, that is interdigitated electrodes based characterization of cancer tissues. So here I'm also talking about the breast cancer tissues as well. ACU8 was used, right? So let me know which of the following is not correct. So ACU8 is a positive photoresist, ACU8 is a negative PR, or ACU8 is is for PR addition. So what is SU8? SU8 is a positive photoresist, SU8 is a negative photoresist, or SU8 is used for PR addition.
Positive photoresist, sir.
Yeah. So SU8 is a positive photoresist, right?
Sir, I posted one question in
No, so
by
like
using
why do you think it's a positive photoresist?
exposed region is stronger in UV and unexposed region is weaker, sir.
The exposed region is stronger and the unexposed region is weaker, right? So you are creating a direct copy of that. Is it correct?
No, sir. When I listen and I understand only, I will say.
Yeah. SU8 is a negative photoresist, right? Yeah, so what was your question? Can
Sir,
we deposit
by
CNT?
using
Yeah, obviously, we can use that. Yes, we can use CNT as a conductive element as well and as a sensing element as well. People have been using CNT like for a long, long time. And like recently, people have been started using 2D materials as well. Like, you know about 2D materials, 2D, 3D materials, right?
yes,
So
sir.
people have been using 2D materials as well, like MOS2, like those are the very like common ones, MOSE2 and these kind of a things. People have been started using that. People have been researching on CNTs as well. So there are obviously like advantages and disadvantages, and based on that, you need to choose like which of the techniques or which of the materials you need to use for your specific use case. But like there are several like trade-offs as well. So like if you can bear the trade-off, you can use it. Like if you even for CNT, I would say like I'm not entirely sure, but for several like sensors as well, we get a better response in place of like these normal things. So like so if we are using CNT, we can get a much better response as well in several devices. Like I have read so many studies and everything. I'm not currently working on nanotubes or any kind of a nano thing, so like nano dots or something like that. But what I have read is that in for many similar kind of a device structures and everything, CNT perform better. So if anybody of you have any questions, let me know. Otherwise, we'll end the session here.
No questions, sir. Thank you.
Yeah.
Thank you.
And best of luck for you. So like
Yeah.
try to just remember the basics and everything. It will be enough.
Yes, yes. Okay, I understand. I
Yeah.
appreciate that.
Yeah,
So
yeah,
thank
sure,
you.
sure. So thank you everyone.